Yes, you got it. Just yeah, just come inside.
How about you? You really see the oscilloscope? You see the screen? No? If you don't see the screen, make some room. Go back. Everybody goes back a little bit. And maybe then you go there, then you see something. Otherwise you won't see anything. Okay, very good. That's yours? No? Yours? Okay. Let's put it here, then you can see it. So what we will do today is we will start with task 1, natural frequency and mode shapes. And this is optional. We will not be able to make that in time, so it's just there for you to read through it and to look at it, what it could be. We could discuss it if you want, but we will not be able to make the experiment. We will not have enough time for that. So, mode shapes. So you had mode shapes this morning, I guess, and you know that every deformation of every physical body can be described by mode shapes, and that the sum of all mode shapes, that means an infinite number of mode shapes, is always able to represent any deformation of everything. Okay? So, and usually the first significant mode shapes, so for example an aircraft, we would represent the deformation of an aircraft by using all mode shapes up to frequencies of 60 Hertz, for example. That would be usually a good value. Maybe not sufficient if you go for supersonic, but for transonic and subsonic, 60 Hertz, for example, will usually do the trick. So now, the first thing before we can do active vibration control is we need to know how it vibrates. So we need to know the modes, we need to know the mode shapes and the eigenfrequencies. So, and today we try to determine that experimentally for such a beam. And I already showed you, so for those who were here in time, I already showed you that by simple doing something like this, you can see the frequency. And you can also measure it with an oscilloscope, right? So like this, you can see how it moves, and you see that it is it's almost a sine, right? So it's a harmonic signal, and that means it's probably only one frequency, or at least one dominant frequency. And now if I do like this, I can shift the cursors to the peaks. Now the two cursors are on two peaks. If I want to increase the quality of that measurement, I take not one peak but several peaks and divide by the peaks, because then the accuracy increases, obviously. And then here I can already read that the delta x, so the delta in time is 1.134 milliseconds, and that translates to 7.462 Hertz. So the first eigenfrequency is about 7.5 Hertz. So now the question is, how do I determine the others? Do you have ideas?
If we have signal, we can take Fourier transform of that.
Good. Yes. But would that signal be sufficient?
No, the complete signal.
What is the complete signal?
A complete signal when vibration starts and it completely dies.
Okay, but if I do really something like okay, let me put start. If I do something like this, do you think this is a complete signal?
No.
No?
It will be covered in full window.
Because it's just a harmonic vibration in the first eigenmode, right?
Yeah.
Okay, and how do you suggest we can change that? How we can get a complete signal? What could I do? Okay, so if I for example would now use this piezo patch and put a harmonic signal on it, it would obviously also react with the same frequency, right? But there are other signals such as sweep, burst, or impulse, which cover more than just one single frequency. They cover multiple frequencies. And for example, an impulse, like the Dirac impulse, you know that, right? A Dirac impulse covers all frequencies because it's a sharp. Yeah? Okay. If you don't know that, maybe we have to go into that or you have to go into that at some other time, but a Dirac impulse covers all frequencies. So this is what we can do, but more precise, and for example, in I think still until today, for a modal analysis of an aircraft, for example, you would really do a single frequency, was heißt denn Erregung? Attenuation, yeah. And this you do by using a sine, so a harmonic signal, and then you slowly change or increase the frequency, and you look what happens to the experiment. So this is what we will do now. What is also written in the task sheet, we will look whether we can detect the eigenfrequencies of at least the first and the second mode shape. The third probably will be too high in this setup to get it done due to various factors. But the first two we want to have, and if we have them, then we try to get at least one mode shape by switching the laser from point to point, measuring these distances, and then measuring the deflection along the axis for each mode shape by looking at the maximum deflection while we have the sign on the first piezo patch.
First case we have sign first piezo patch. Second case we have sign in two piezo patch or the second.
No. We stay at one piezo patch. Okay. We always only use one piezo patch today, but then we increase the frequency, and when we come close to the first eigenfrequency, it should start shaking a lot. And then when we further increase the frequency, it should be still again. And then when we come close to the second eigenfrequency, it really should start vibrating again. And then after that, it should lose. And now, if we, for example, have the laser here and we go to the first and the second eigenfrequency, then we can see measure the amplitude here. And then we shift the laser to here, go to the first and then to the second eigenfrequency, and then measure the amplitude here, then here and here. Yes, and then if we then plot the maximum amplitude here, and here, for each mode, or for each eigenfrequency, then we will see a mode shape maybe like this, so as the first one, but the second one should look more like this. So that's the strong deflection, but it will be very small. It will be only like this maybe, but still the laser should be able to cover it. Okay, good. So we again divide the groups. We have identical setups, group A here, group B there. We start and we look where we come. Mein Englisch versagt heute ein bisschen. Ich weiß nicht warum. How's this? Ja. Okay, so and the maximum voltages we want to use is for the first eigenmode written here. So again, this is the maximum voltage, that's the amplification, so that's the control voltage. Same thing as yesterday. Did you also see that? The voltage, control voltage, you got that? Like yesterday, same thing like yesterday. Okay, so first thing, steady state, frequency, do you know it? So you see there's the table, and so the first thing is the excitation voltage, I gave you that. But then in the second block, there's the static state frequency, first eigenfrequency, second and third we will not manage to do. But what is the static state eigenfrequency?
And there is no deflection in the beam.
So what's static state? What frequency should that be? 0. Good. That's the first one, you already got that. And the maximum tip deflection will be whatever the laser is right now. Okay, and then again we do the difference by putting the tip deflection of the second to third by showing the laser, and then we'll subtract.
First we will identify the first mode.
Yes. Yes.
Then we will plot the mode shape.
Yes. No. First you identify first and second eigenfrequency, and then you identify the mode shapes by going into the first eigenfrequency and then into the second for each point. And measure the amplitude.
How will identify second mode frequency?
Sorry?
How will identify the second mode frequency?
Yes, we need to use that. So
Excite the PCT and
yes, we excite the PCT, and the control voltage is given in the upper box. 20 volts, so 0.1 control volt. Okay, sine, with a sine. Not DC, but a sine, a harmonic signal. Okay, go for it. Before you activate this, please ask. Okay, first we want to see the eigenfrequencies. So I suggest we start with the tip.
Start with the eigenfrequency.
Start with the eigenfrequency. The sensor should be placed to about 5 volts, so you can go up and down. If you place it to 0 volt, you can only go up. If you place it to 10 volts, you can only go down. Right? Yeah.
5 volt.
We can close the cursor.
Good.
Now you're at 4. Yeah. Maybe you can increase it a little bit to 5 again.
Increase downward.
No. Just use the wheel, yeah. And have a look here.
Yes. Increase 4.5.
कम हो रहा है ये 5 तक है।
तो और नीचे गई. Down.
No, now you're going down. You need to go up.
Up. Need to up. Up. Yes. Keep going. Yes, keep going.
Can you see the value so you know what you're doing?
Just checking the green color.
It's increasing right now. It's up to 4.8. We have to make it. But it is out of
It should be something like 5.
5. Okay. It is out of range.
No, it's not out of range.
Not out of the range?
No, it's green. It's fine.
It's green?
Yeah, okay.
Now green.
Yeah,
Yes,
now
5
it's 5.0.
Oh, okay.
Yeah.
Okay, good enough.
Yeah.
So maybe you now put in the static state frequency.
No. 5 volt.
The static state frequency. What is the static state frequency?
0.
Yes, thank you. 0. Exactly. So you put in 0. Yeah. And now you put in the maximum tip deflection at static state, which is?
5 volts.
Yes, whatever, so more specific maybe.
4.98 volt.
Okay. And now you set the function generator to a frequency you expect will be the first eigenfrequency and try if you can find it.
Yes, we will test.
Okay.
So, when is the option for function generator?
Somebody knows. Somebody of you knows. Somebody did it yesterday. You did all of that yesterday. Where's your colleague from yesterday who did everything so good? There she is. No. But she can explain to you. She can explain to you. They need to know how they can set the function generator.
Who wants to?
Sorry, I don't know. It's one of the group. Okay, and now what is the frequency?
46.5 Hz.
Where do you want to start? With what frequency you want to start to measure the first eigenfrequency? You should start below and then slightly increase it until you see movement.
It is 46.5 something hertz.
I don't know. So we measured the first eigenfrequency, Choban, right? Did we? Yeah, so about 7. So you should start below 7. Somewhere below 7. Maybe you start with 6? 5, 6, something? And what is the amplitude? And what is the amplitude?
Amplitude.
And what is the control amplitude you're supposed to use? It's there on in the upper box. There's a maximum control voltage. Point. Is it set to 0.1? And the function generator is moving?
Yeah.
Okay, so somebody hit the button. Something happening?
No, this is not, I think, in a good position, sir. It is flickering enough.
Doesn't matter.
Blinking.
Yeah, I think it's okay. I don't know why it's blinking, but it should be fine.
Someone
It's not red. It's not red. it's not red, it's fine, so probably it's measuring. So I don't see anything happen. Are you still on the function generator? Now you can do the following thing. You hit frequency, and now you use this and watch the frequency. Turn that and watch the frequency. Yeah, turn it. And now you go until you see that you reach the first eigenmode, and you will see that because the laser will do something. I don't see movement.
Why this line
Go. Go.
7 के ऊपर जाएगा
7 के ऊपर आएगा
7 के आसपास
हमने किया था 7 के ऊपर आएगा
Oh, now happens. Now something happens, right? And look at the beam. But it's not a good harmonic vibration yet.
No, I think sometimes no, not like see sometimes getting some
Yeah, I think you have to go a little higher.
higher. 7.5.
Just come right and
Don't always do.
Ooh, now we're going somewhere. Ah, it's still not good. Where are you? Go a little bit higher. Just maybe 1 or 2.
7.5.
And now look at it.
yeah, slowly.
Where are we?
7.5.
7.5.
No, it's much more.
And now it stays, right?
Yes, it's just text.
So that's looking good? You guess that could be an eigenfrequency? No? Yes? Yes. So the eigenfrequency we can detect because the amplitude now, I mean, what happens if you go higher with the frequency? Nothing, right? Nothing. The voltage is the same. Or at least we have verdammt, eine Schwebung. If two frequencies are very close, then you will get something like it goes up and down and up and down. And this is what we see now more or less. And then if we go even higher, then it basically stops. So if we go back and we excite directly in this, what was it, 7.5?
Yeah.
If we excite directly in the eigenfrequency, then we get huge amplitudes. Okay? So, and what we can do next is, if we hit the acquire, and this is a time-based signal, right? And let me zoom into the, no.
No better.
This is a time-based signal, right? Let's go to XY and see what happens. Oh no, not XY, sorry. To Y, that's XY. Do you see what I see? If you're in the eigenfrequency and you plot the one signal over the other signal, so the excitation over the amplitude, what you will see is that. You will see a circle. It's called Lissajous-Figuren, Lissajous figures, after the woman who first saw these figures. And if you, now I will again increase frequency just a little bit and look at the circle. It collapses, right? And it changes direction and everything. So now I go back to the eigenfrequency, 7.5. We have just to wait for a second, and then it will rise again. And below that, same thing, the circle collapses completely. So if you're in the eigenfrequency, in the XY diagram, you should be able to see a circle, almost perfect circle. Yeah. And this is actually because the angle between excitation and deflection should be always like 45 degree, minus 45 degree, and this is why you get the circle. So this is the reason behind it. Yeah. Okay, so this is the first eigenfrequency, and now have a look for the second eigenfrequency. I suggest to go to acquire and to start in the time-based signal maybe again with rho. And I also tell you right now, you probably have to look somewhere above 40 Hertz, otherwise we will search kind of long time for the second eigenfrequency. So maybe start from 40, looking for the second eigenfrequency. How about you? Oh, what are you doing?
Frequency
Mm-hmm.
6.9.
Mm-hmm.
You can see this from here also.
Is it not written there?
Same.
6.9, okay.
Just to check.
Just to check, okay. I think the machine works though. Okay, but I don't see that you excite at any eigenfrequency right now, right? So let's do that. Yes, go for it. Start. Maybe we shut the cursor. And now go to the function generator and set it to somewhere below the first eigenfrequency. Use a sign somewhere below the first eigenfrequency and don't exceed the control voltage. You may now exceed the control voltage to not 0.1 but more like 0.2. Exactly. Sie hat zu viel auf 5 Volt gesetzt, weil that's why I shut it down before you did something. Yeah, that happens. It's just because you didn't hit the. It's very hard to hit the millivolt button. So 200. You really need to be precise, and then it works. Okay. So now I don't see something. Now I start seeing something. Yeah, and maybe we have to increase that signal as well. Let's see, is that possible? But then we have to go down. Increase that again. Ooh. Where is it? Now increase the laser signal a little bit so you can see something. So where are you right now?
40.
So now you see whether you can actually find the second eigenfrequency. Just to check, if you go not touch any contacts, but if you touch the aluminum, no, there's nothing. So 40 is not yet it. You now slowly increase again the frequency until you find the eigenfrequency, right? So you go again, this is the frequency, right? And now very slowly, see if you see something. And if you go to XY, the circle should be there if you're in the frequency. Where are we?
Here set 6.8.
6.8, okay. 100 millivolts. 100 millivolts, 100 millivolts, 0.1, 6.8 hertz. Good. Go for it. See what happens. It is vibrating, but I don't like it. Maybe you increase the... So, oh, I didn't tell you how to do that. You go to frequency, and now you're able to use this wheel to slowly increase the frequency.
6.9.
And yet, now you look at the signal, and you see what happens. It is like this. So it's not an harmonic signal. The answer is, so, increase it.
So it is increasing by 0.1.
Hmm?
It is increasing.
Yeah, I know. There's no smaller option, unfortunate. More.
Still.
Getting closer, I guess. Getting better. Maybe add one more. Let's see. Oh, now it starts. Yeah, now it starts. And if the answer is also harmonic, so if the displacement is a harmonic signal, I don't see it, but you see it, then you're in. Okay, let me check. And now go one ahead and see. Does it reduce?
Yeah.
Okay, so then you have been in. So go back to the eigenfrequency, please.
6.9.
No. The eigenfrequency was what you now measured. 7 point, I don't know.
7.2.
So is it? But you're not in. Go. No. We're not done. We're not done. Go back in.
Okay.
Go back in.
So now it's 7.3 again.
Yeah, that's looking better.
Now it is decreasing. 7.3 is given.
Then 7.3, yes? Just wait for a second. Now let's see, I'll show you something. If you now go, okay, first of all, we need to get that a little bit down. More down, more down, more down. Yeah, like that. Now we scale in to make both signals a bit higher, and we put it down until they overlay. Something like this.
They're in different phase.
Yes! But they have a, no, they are, yes? How much?
Maybe not 180, but
Less than 5.
How much?
stop and check.
Just look at it. In a second? In a second?
1 by 4. Matlab T by 4.
So 360 by 4?
360.
So the 180 by 4. What is that?
That's the phase shift.
Yeah.
Sorry?
45.
45 degree, perfect. If you're in the eigenfrequency, you will exactly see a phase delay of 45 degree. Let's get it running again. Let's go to acquire. And now let's not go to roll, but let's go to XY.
Phase potato.
So if you see a perfect circle, you're in the eigenfrequency. So it's not yet completely perfect, right? Let's see what happens in this direction. Oh, sorry, that was wrong. Let's see if we go to 7.4. No, the circle collapses, right?
Reduce.
Yes, so 7.3 or maybe 7.2. Let's check that for a second. If the circle becomes wider, I mean, we can always increase also the signal. Oh, sorry, that was me. No.
Punkt 3, näher kommen wir nicht ran wahrscheinlich.
Nee. So the problem is, I guess, that we cannot really. So this is the best we can do. It's still slightly like this. It should be perfectly on this, but that's not exact enough because we can only do 7.3, and probably it's something like 7.35, for example. So then it would be a perfect circle. No, it will not work. I tried. Good idea, but it will not work. Okay, so this is the first eigenfrequency, and now your job is to get the second eigenfrequency. And what you do is you increase now the frequency, and see so it will stop vibrating, and then it needs to start vibrate again. And at the point where it starts, we can go to acquire, can go back to roll. You see that? And a small hint from my side, it will be somewhere, push G1, and now you can increase. But it will be somewhere above 40 hertz. So you will take a very long time to find it if you do not start with somewhere like 40 hertz. You could also just roll it. Yeah, we're still at high voltage. Yeah, that's important. Okay, then for you, what was the question? Will you be able to find it?
No.
Okay.
Up to 50 hertz.
Okay, that's far too high.
Should we increase?
Oh, but something happens, right?
Something is happening, but should we increase the voltage?
No.
No.
Did you see what happened with the frequency? Mm-hmm. Yep. You see that this is still not good, right? So now, what happened now? Oh, that was me, I think. Now, you see what I did? I did like this, and it started shaking in the first eigenfrequency. And the second eigenfrequency is overlaying. You see that?
Okay.
Okay. So we need to wait for a second, sorry. Because like that I can't see anything. If you touch the table, then we are, you see the system. Yeah. But maybe right now, and now we, I think, have to increase a little bit and see that we get rid of the second one. Now we excite the second again, that's bad. I'm also not sure how to damp it.
Actually, we have tried up to 50, I think, but we didn't. Let's see.
No, it should be somewhere around here. I can check for you, and then... Does it... no. No, it's higher. Okay. Should be more in the direction of 46 hertz. So at least now we lose
Around
the...
45 we got, but like this only.
Okay. But this is not too bad, right?
Around 45 there was something, but as we increased, there was...
So the problem is we always also, you hear this clack clack? So always when I change the frequency, then I give like a small impulse. So I always, I have work on all eigenforms or on all eigenfrequencies. So I also get something towards the first eigenform. That's now we're getting close. You see how it becomes, the signal becomes wider. Now we still have some Schwebung, whatever that is. I think that is already looking pretty good. So let's wait for a second. I don't think we will find out more. So we will, can we put that up a little bit? Up a little bit. Up a little bit. Okay, something like here. Okay, and if we now go again to the XY plot, let's see.
XY plot, it is not...
It's not a perfect circle because we can zoom in here, but it's not it doesn't have a slope like this or like this. So now you're pretty much in the eigenfrequency. I don't think you will get it much better since the amplitude is really small. And now if you have a look at the beam, I'm not sure if you can see it.
Yeah, it's vibrating, I think.
No, it is vibrating. From here we can see.
Yes. Okay.
This is like...
So this is probably...
No, from here you can see. You have specs also. No? Come here. Come here. You will see from here. It is vibrating. Yeah, from here.
If you very carefully touch here.
Yes.
Yes.
Similar is
Yeah.
No, you come here. You ask the question. That is, you can see.
Okay. So now we got the second eigenfrequency. And if that happens to a structure a lot, that may damage the structure after some time, right? Okay. So now you know both frequency. Did you note them down? Did you write them down?
First was like 7.5, second one is like 46.7.
Tip Deflection fehlt, brauchen die. Also die Frequenzen.
And ideally now you also note the tip deflection, the maximum tip deflection. So do you have an idea how you do that? I can show you. So we go back to acquire and go back to roll. I don't know why we have these two signals. We cannot get really rid of that. But you have a mean, right? You have the mean voltage of the blue signal. Let's get down the function generator for a second. And now let's go to stop.
Okay.
And now let's go to cursor. And now let's go to a manual.
4.96.
Look. Okay. To a YY cursor. And now ideally, source A is channel 2, source B is channel 2. And now, do I move it or not? Oh, come on, no.
Okay. Now fine.
So now we, for example, take these two tips here. Can you see them?
Yes.
And now the lower one I place on the same tips like this. Okay? And now you've got two values. And you got the difference. And the difference is 245 millivolts, right? And if you, this is 2 times the tip deflection. So if you divide that by half, you've got the tip deflection, right?
So 122.5. 122.5.
Millivolt. Yeah. Exactly. And then, so you have to write volt in there. So it's 0.1225. And now I think we have to do a little trick, otherwise it won't work. We have to, since here it's subtracted, I think here we have to add the 0 value. But that's just for calculations. And now it actually works. So you have like this. Okay, we can also do, wait a second. So don't be confused by that. That's just for calculations. 0.1225 millimeter, that's what it should be. You didn't do that, by the way, here. We could do that as well, the tip deflection. But now we basically can go, so maybe go back to the first eigenmode, I think. Can you enter in the generator the first eigenmode again? But use a control voltage of 0.1 volt. How's it going? Have you been able to find the... Yes. Have you been able to find the second eigenmode?
Not yet.
Okay. So where did you go? Where did you arrive?
Around 53.
No, then you're above, well above the second eigenmode. So I suggest to look at 40, probably 44.5 to 47 somewhere. Because the experiment's slightly different. The beams are a little bit bent, for example, and that will change the mode. So it's not exactly identical. And you will probably not see it. So you have to look what you see here. Should we zoom in a little bit? Should we zoom in a little bit? No, not here. This is just a generator signal. Yeah. Okay. And let's go down a little bit to get it on 1. Zoom in a little bit. Go down a little bit. Where are we? Yeah. Now we start seeing something, right? So I suggest to leave it like this. You're not there, because the frequency of the answer is very different from the frequency. So now again, if you go here, yeah, exactly, and now you, sorry. And now you rotate a little bit and try to look somewhere above maybe 43, 44, very closely. You will not see it here. The deflection will, but you will see it here. The frequency should become the same, and then we should see the circle in the other diagram. Did you change the control voltage to 0.1?
Change, okay, this is coming like that only. From where to zoom out? I forgot.
Here,
Yeah,
like
I was
this,
doing,
but then
Yeah.
we have to put it up a little
Yeah,
bit.
this one I know.
Yeah, just a second. Here.
This
So.
one is.
And now you're in the eigenfrequency, so just hit stop. Now hit cursor,
Cursor.
and now you do the YY is correct, is good?
Yes.
Yes, and then you can already, I don't know, if you now turn that, you can do the first one, right?
Yeah.
And then you press the button once, and you see, look, here I'm at AY. Now I press the button once,
Okay.
I'm at BY.
Okay. Let me do it.
And here you again have to enter a formula, that value negative the one they tell you.
It's a 8.5. So it is around 8.5.
I have no idea, by half, you know?
It is first.
So here it's minus 8.5, what's the half of that? Tell him. No, not zero, really 4.25. Volt, yes, not millivolt. And now you see, and maybe this value you can, yeah, it doesn't matter. Anyway, you see that so static state 0, first eigenmode tip deflection 4.25, second mode tip deflection only 0.12 millimeter. So the higher the frequency goes, the smaller the deflections will be probably. Okay? And now what you, thank you. Now what you could do is, now you do the same thing here, 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 and here.
No, please come. You will. No. We are.
Yes.
No. Mark is